So we said that calculus is about two main ideas, and this is one of them, that you know how fast a quantity is changing, you want to know how much of that quantity you have. So knowing how fast something is changing is knowing its rate of change function, right? So knowing how fast a quantity is changing means you know its rate of change function. Wanting to know how much of it you have would be wanting to determine either a net accumulation or its twin, or its twin brother total accumulation function. So this is a review from last time. So we know how fast a quantity is changing. We want to know how much of it we have. So either how much it's changed since the reference point, or the total accumulation since that reference point, which could include an initial amount. So it could include an initial amount. Okay, and so we talked about, so we have this this rate of change function. No hand up. Yeah. So you can just keep it on this side right here. But don't write anything yet. The side with less stuff on it. But don't write anything yet. You don't need to look at it. Okay. So this is a rate of change function for the rate of change of volume of oil being expelled into the ocean, say, from a leaking oil rig. Okay, begins leaking at t equals 0 days. Okay, so we said that if that's the rate and there was no oil in the ocean to start with, then maybe this the volume of oil, the quantity, the amount of oil, and the accumulation of oil in the ocean might look something like this. Okay, and this is where we left off last time. Okay. So what's our endeavor? So again, we're talking about, you know how fast something is changing. We want to know how much of it is. So if we were given that rate of change function, could we create, build this accumulation function? That's our goal. If we were given that rate of change function, can we build that accumulation function? Well, this is not an easy task because that rate of change function is changing, right? With your tub problem, the one I just showed on the previous screen. What made this so easy? What made it so easy to figure out accumulation from rate? Constant rate of change. With constant rate of change, wow, things are really easy. And you just all did this about 5 minutes, right? But now, with a changing rate function, it's a whole another ballgame. It's like, how do we know how much has accumulated? How many? Because as soon as a little time goes by, we're at a different rate. Right? As soon as a little time goes by, we have a different rate. So how can we figure out how much is accumulated? So this is where we're starting this journey of figuring that out. It's not a quick, easy question. Okay, so let's talk about this graph and this statement. So I have a statement that the rate of change, or the value of the function at 0.7 equals 9.68. How does that just relate to the graph? So that statement right there, what does it relate to or mean for the graph? What is it about the graph that statement is? Yeah?
The rate of change at 0.7 is 9.68.
Okay, so but how does it relate to the graph? What about the graph is showing that? The displayed graph. Is it the whole displayed graph? No, what is it? It's a point, right? It's a point. So watch the graph. Here we go. At 0.7, the rate of change is 9.68. And how do we see that that rate of change is 9.68? Do we zoom in? Oh, where am I? If it's a rate of change graph, how do we get the rate of change? If it's a function, rate of change function, how do we get the rate of change? We have to zoom in and do dy over dx. No. What do we need? All we need is what? Y value. That's what a rate of change function is. The dependent variable, those are values of rate of change. So we just get the y value, and that's the rate of change at the particular value of the independent that we have. Okay? And so then, what does that mean in this context? And she articulated it very well. It means that at the moment, 0.7 days, oil leaked at essentially a constant rate of 9.68 meters cubed per day. Okay? Not at the instant. At the instant 0.7 days, there's no rate of change because rate of change needs some kind of change, right? So it's not at the instant, but we need a little change around 0.7 that allows us to talk about rate of change, 9.68. Okay, so if I zoom in on here, I'm zoomed in on 0.7. I'm zoomed in on 0.7 days. So I'm just showing a very small moment from 0.697 to 0.703 days. I'm showing this very small moment. And this red graph I'm showing is the actual rate of change function. What would this statement suggest for the graph? That at 0.7 days, the oil leaked at essentially a constant rate of 9.68 meters cubed per day. So how could we apply this meaning of our rate of change of 9.68 into this moment diagram? What would it look like? Is that showing a constant rate of change in this moment? That red graph?
No.
Is it showing a constant rate? This is a rate of change graph. Is that showing a constant rate of change?
No.
No, why not?
Because it's not flat.
Yeah, this is an accumulation graph. We're not just looking for something linear. Now we've got a rate of change graph, so constant rate of change would be
Flat.
horizontal, right? So that this meaning that we have an essentially a constant rate at 9.68, we want to think about like this, constant rate for the moment, right? This is a very small moment in time. And so that this correspondence point, 0.7, 9.68, we want to conceive like this, that in a very small moment, we have a constant rate of change of 9.68. Does that make sense? So we got a rate of change graph now, so a constant rate of change would be a horizontal graph, but only, so but in a very small moment here of time. Okay, so we're going to use that and use all this stuff we've been learning, right? Now we're going to, for this little moment, we want to build the accumulation. We want to build some accumulation using what we've learned and using the fact that in this moment, we're going to assume this constant rate of change in this moment. Why? Because it's easy with constant rate of change, right? The tub problem, right? And all this math we've been learning about constant rate of change, we can deal with that. It's when the rate changes that we have difficulty. So we got this constant rate now, and so now we can answer some questions. So suppose at 0.7, the total accumulation of oil is 13.15 meters cubed, okay? So now let's say we want to figure out what? The accumulation of oil a little bit later at 0.7013. 0.7013 days. Okay? What would dx be? What would dv be? And then can we find that a little amount? We have all the tools. We've been working on this the last couple of weeks. We have all the tools. So what would dx be? What would dv be? And what would this volume of oil be at 0.7013 days based on a constant rate of 9.68 in this moment? All right, so this is the other side of your sheet, the side with more writing on it. So you can use the upper right-hand corner just as blank space if you want it. You're going to do some calculations, and you can use GC for that if you want, or a handheld. It's fine. But you can use that upper space to write out some calculations, and then you're going to illustrate down here in the lower right. Okay. What are we doing? We're building a little accumulation from a moment of time, knowing the rate function, knowing the rate, right? So find dx, find dv, find that, illustrate it. It's all stuff we've done before. It's all stuff we've done before. Can you apply it now? Go, see how it goes. Is that better? Okay, let's see how we did. Where's Rashid? Al Farsi. Did you get dx? Well, tell me what dx is, Rashid. 0 point. 0 point what? 70? Well, we want dx, right? So what is x changing from? X is changing from what to what?
0.7013
Right. It's changing from 0.7 to 0.7013. So final value of x minus initial would give us 0.0013. That's right. That's your dx in this implied, right? It's implied. If we're starting it, we know what v of 0.7 is. We want v of 0.7013. Well, then the x changes by 0.0013 is the change in x, final minus initial. Okay? And then how are we going to find dv? Where's Ahmed Al-Bakri? Ahmed, did you find dv? How'd you do it? Good. Times what? No, times dx, right? Right. So here, we've got constant rate of change. We've got constant rate of change. What does the 9.68 mean? It means for any change in time, the change in volume is 9.68 times that change in time. And we're going to use it now. Right? So we're going to say 9.68 times the change in x. And you get a number for that. What number do you get? 0.013. Is that what it turns out to be? 126. 126 we'll go with. Okay, so now we want to know what the final volume of volume is after this change in time. How do we find the final value of volume after this change in time? Where's Dylan Jacob? Dylan. Where are you? Oh, right in front there, okay? So what principle are we going to use to find this final volume? Okay. Okay, so what's that principle? To get the final value of a quantity, we take the initial and add the change, right? Take the initial value of the quantity, which was the 13.15. We're going to add the change, which we got was, he said the rate times the change in x. That's fine. We've already calculated it, so I'll write it here. And what do we get? So I'll go with 163. Is that okay? So now let's illustrate that. We started at 0.7 days, 13.15 meters cubed expelled. And what happened? We had a change at 0.013. And I think that takes me to right about here. dx is our 0.0013. As a result of that change in x at this constant rate, our change in volume was up to here. $13.163, which came from what? mdx. And that took us to a final volume of what? The original 13.15 plus the change 0.0126. And so then the coordinates of the final point are? Did I make a mistake or you have a question?
Isn't dv just the 0.0126, not the value of 13.1?
Yeah. Sorry. You were all thinking that, right? dv, sorry, I was looking down here. dv is the 0.0126. Thank you. Right? I wrote down what the final value is. So this is 0.07013 days elapsed. The new volume is 13.163 meters cubed. So you can practice that again at home for this one, right? So I'm not selling. Yeah, practice that at home. But another thing we want to talk about is, let's suppose this was any point. X, comma, v of x. How could I represent now any point in this moment? Could you represent any point in this moment? And that's also something we've worked on. So if we want to know what, we want to know the final value of volume here, or final value of a quantity, it's going to equal initial plus the change. Initial plus the change. So we could start with our initial of 13, what was it? 13.15 plus, how much does the volume change when we change x from 0.7 to any x? So we need what? So how much does that volume change? We need the little change in volume as x changes from 0.7 to any x in this moment. Yes, sir?
X minus 0.7.
X minus 0.7. And then what's the resulting change in volume? The change in x times 9.68. So in this moment, we can write now every correspondence point of days and resulting volume in the ocean this way, right? So because the change in x is x minus 0.7, the change in volume would be the constant rate times the change in x. That change in volume plus the initial volume gives you your final volume. And that would represent, the thing in the blue box now represents every correspondence point. Every correspondence point in this moment. Okay, so now we're really starting to use this stuff. We're starting to do calculus now, okay?